I think, yeah, there is a kind of a super Cold War because all these things take place in super cooled dilution chambers. So like there is a super Cold War going on in many ways. The biggest difference between, and I think there is actually a either an analyst or even a senior member of the US military who came out and said, yeah, this is as impactful potentially as atomic warfare.
In today's interview, I'm talking to Dr. Mark Carney. This is an amazing conversation. I really enjoyed it. I'm sure, and I hope that everybody is going to enjoy it, especially if you have a mathematical mind or you're a mathematician. Mark is apart from being a mathematician, he's also a magician and a musician, and you name it, you'll hear all about it in the interview. We cover everything from quantum computing and cybersecurity to computation with tilings of the plane to quantum-inspired AI, the quantum Cold War, the three quantum revolutions, swarm computing, graph theory, and cybersecurity. And of course, we touch on our favorite topic on this podcast, namely academy versus industry, how Mark transitioned from academy to industry and how he is applying mathematics in industry. Welcome and enjoy. Oh yeah, and in this conversation, we mentioned a lot of books, articles, people's names, technical terms, and I tried my best to collect all the links in the description below. Hello, Mark. Welcome to Manifold Solutions podcast. Mark Carney is a senior cybersecurity researcher and lead for quantum and AI at the Santander Global. And he's also a co-founder and the CTO of Quantum Village. He did his PhD on computability theory at the University of Leeds. And yeah, there's going to be a lot to talk about already from these things.
It's very nice to be here. Thank you for having me.
I have to say, you are an amazing person. Like when we met, you told me that you are a magician. You taught me magic tricks, which I, by the way, later showed to many people, and they were all blown away. I practiced them actually. You're a violinist.
I used to be. When I was growing up, I was a music kid, slightly more than I was a math kid. So the music sort of drove me a little bit. I ended up going to Turing School of Music for my A levels in Manchester. So went to this really good music school, and I was like, yeah, I'm going to be a musician. And then about a couple of years into being a musician, I was like, this is not the most intellectually stimulating thing for me personally. And so I kind of pursued the other kind of passion that I had, which was for mathematics and for understanding this thing called computation, which was everywhere, and I was like trying to make sense of it all. So trying to sort of that personal journey was like sort of, oh, hey, I'm going to go and just do this thing. And that was a whole thing, getting into a maths course with a music undergraduate. Because I actually did my undergraduate in music as well.
Oh, I didn't know that. Okay, so you have a real degree. Did you ever do something where music and math are together? Did you ever like study music? Yeah.
Yeah. So while I was doing my music undergraduate, I actually did some math courses and some philosophy courses alongside. I did like a philosophy course in logic. I did some after I graduated, I managed to speak to a friend of mine. He's now a professor at Liverpool, Professor Lasse Wimber-Gillen. And he was a lecturer at the time, and he was giving in the UK they're called magic courses. You're probably familiar with. So they are the kind of online distributed kind of talks for postgraduate students. So they'll do short courses on like the course I did. It was complex dynamics that I did. So I was just sitting there, just enjoying it, and I was just really like into it, and it didn't feel at all disjunctive to be going, from a math lecture in the morning to a gig or rehearsal or something in the afternoon and evening. So yeah, I loved it. It was great fun in Liverpool.
Did you ever do like mathematics of music or something along these lines?
I do think about it. I do. There's a guy, the name escapes me, I'm really sorry. But he's been doing like sort of musical set theory, which is kind of fun. And if you've ever heard of Schenkerian analysis, that's quite mathematical in the way that you pick apart what's going on, taking, you know, collections of notes with intention and then how you categorize what's going on.
Mm.
And then I've done some kind of more edgier stuff like building synthesizers I enjoyed, but like on the software side more. Because there you get to like really play with it. I've even made some quantum ones recently because like the mathematics is quite fun and quite straightforward. And so it's like, okay, let's play musically in this Hilbert space that we found ourselves in. So like
Ah, so like generating music out of mathematical ideas.
yeah, and I actually did some under a pseudonym, which I won't give away because I might want to use it again. But I did like some algo rave stuff, which is great fun because you're just there typing code, and it's all in CloJet, but there's brackets everywhere. It's quite Lisp-like as a language,
Mm.
and then you're typing, and then it's going to a back-end sound engine. There's many you can choose from, and so you're submitting like an algorithm, a line of code, and then it becomes sound. And then you can go, oh, what do I want to do with that next? And then you can sort of shape it around. So yeah, music and mathematics feel very interchangeable to me anyway. Same with programming. It feels very like quite natural to go, hey, I've got this thing I want to do. Um, how do I do that then? Because it's not always obvious how to, play a particular piece or how to, solve a particular problem.
There are many parallels. Like, of course, you can do this, and you can analyze sound with Fourier analysis, but
Mhm.
also I think classical music and pure mathematics somehow are connected in the way they're both abstract and intellectually stimulating. Einstein used to play violin,
That's right. And
and
there's a moment recorded in history of him playing with a famous composer, but the name escapes me. Wasn't Schoenberg? Who was it? Can't remember.
right, we can find it out later. Put some links into the notes.
Sure.
And there is a book called the I'm not sure what's the name in English. It's the Game of Glass. Oof. It's about the future utopia where everything has been figured out. People don't have anything to do. All they do is they play this strange game, but they also play music, I think, in that book.
Okay, I can see that. I can
It's
see that.
like the
It's
only things
interesting.
that are left after AI has,
Solved everything
producing
else.
the
Yeah.
food and energy. So
It's interesting because like some of the classical we talk about classical music, but some of the classical theorists like Immanuel Kant thought that music was the finest of like the passive arts. So he likened
mm,
music to like the perfect frame around a painting or the perfect hedge around a garden. And I've always found that to be kind of not to disagree too much with, people who are revered in antiquity, but I've always found that a little bit belittling of music. I think that actually music can be very intellectually engaging. I remember reading when I was quite young, Gödel, Escher, Bach, and that's really something that fired a lot of passion for logic and getting this idea that you can have these formal systems, but then there's these limitations and there are these corners where you can't quite get out in a sense. You can create something that you can't quite get to. It's kind of really interesting notions of what I now know to be, unprovability and independence results, and how you can apply that to other things. But I always found it really interesting. Like, how do you, in many ways, like mathematics has this intrinsically creative component that seems to be beaten out of us as children, and we have to come to it
yeah,
later to try and find out that actually, there are these very beautiful proofs. Even so far as I think I recently got a updated edition of the proofs from the book, by famed for Erdős's prose of "This is a proof from the book." You've touched this kind of almost ephemeral knowledge that is almost forbidden, but not quite. We've managed to outsmart the gatekeeper
yeah.
one last time.
So just for the listeners who might not know everything, Douglas Hofstadter, the author of Gödel, Escher, Bach, he made a connection between Bach's fugue. How do you
Hmm?
pronounce that, man?
Fugue, fugue, fugue.
Fugue. And Gödel's theorems and Escher's paintings. So Escher had these kind of circular paintings where you have like illusory paintings where you have stairs going around and around. It looks like they are infinity increasing, like in an impossible way. Gödel's theorems, which talk about self-reference, and fugue, where also there's self-reference because the same theme appears on many different layers and in different temporal modalities. And yeah, it's a fascinating book. I have it also on my bookshelf. And Paul Erdős, whose idea is the book, he was like this eccentric mathematician of the last century who is at the same time the prototype of purist who rejected all notion of applied mathematics and didn't want mathematics to have anything to do with anything. And he was one of those who, just closed himself into math his entire life. On the other hand, he was one of the kind of first mathematicians who collaborated a lot. So he introduced this idea in mathematics that you can actually travel around and work with other people, not just sit alone in a room. So he was like
It's interesting because he did move away from that kind of applied view. No, we're going to just deal with the numbers. But he made it a social enterprise in many ways. Like
yeah,
sort of here's a problem, but you can help out too. Famously, of course, engaging Terry Tao,
yeah.
really quite
Uh,
something, really quite amazing. And there's other people that I sort of find myself thinking, oh, I wouldn't mind having a coffee with them, Like Euler, I'd love to have a coffee with Euler. I think that would be really quite something.
yeah. So those people, maybe not Paul Erdős so much, but Euler still was one of those mathematicians who was working directly with the real world.
Yes.
And I recently wrote this post on LinkedIn that there is some forgotten skill of real mathematics, which is not applied mathematics, because applied mathematics is where you take existing mathematics, which already is known to be good in applications, and then you use it as a tool, like statistics. And pure mathematics, which is just Paul Erdős type of mathematics, where you just are in the cloud of abstract beauty. But real mathematics, where you take a problem like the Köningsberg bridges, and then you analyze it and you build from scratch mathematical theory, which is just for that purpose, and then it becomes it gets its own life. So that's why I would also want to have coffee with Euler and many other people for that matter. But I think this is kind of a forgotten, like in modern universities, there's a segregation into applied and pure, and the pure mathematicians are often just ignorant of what mathematics can be used for and not really interested in that. So you did your PhD in quite abstract topics. Well, tilings are found in buildings, and you did you analyzed the computational complexity. How does it work? How do you do computation with tiles?
So
Uh,
the actual proof is
and
in
what's
two
the
parts.
definition of like?
So this is the ability to express any Turing computable function in a tiling set. So if you have a particular tiling and then you can control the first row, that helps you. Um,
Ah,
and then
so
to carry out,
you put the first row, and that
yeah,
forces the rest
yes.
somehow, and that's
And
the
so you
compute.
can, yeah, so you can force a computation using that.
Wow. Yeah, now I understand. Yeah. So
Yeah.
the input to the algorithm is one row of tiles, and the
Hmm.
output is whatever you get when you read it out from
When you tile the plane, and then in
tile
tiling
then.
the plane, then you actually perform the computation.
Do you require that in this definition, do you require that there's always a unique way to continue it?
Uh, in this particular case, yes, because you don't want to have that's the difference between Turing machines and non-deterministic Turing machines, which
Right.
you could do in tilings too. You can
I see.
have with non to go non-deterministic. Suppose you have a particular color that represents a particular state. Instead of having exactly one tile that matches that particular configuration, you can have two.
Hmm.
And so there, the tiler has to make a decision, and so you'd have to enable the tiler, which is the Turing machine is now the tiler, plumbing this infinite bathroom wall. And so you have to allow them to have a coin or a die or something random that they
Hmm.
can flip, and then they could decide which one they put. And
Hmm.
so, yeah, but you can do that with tilings very easily. But to be Turing complete, so this is representing a Turing machine, and you actually end up using elementary cellular automata here because there's a representation of Turing machines in ECA theory, and then you can just code the automata into a tiling set.
Hmm. What
It's great fun. It really is, and here's what you need. Like this is minimal. I don't know of a. I think I had a design for like a more minimal version that only used 8 tiles, but I haven't sat down to finish it yet. But I reckon that you can do it in 8 tiles, no problem.
This reminds me of Paul Erdős's if I remember correctly off the top of my head, you can partition a square into 27 squares which are all different size, but you cannot partition a cube into smaller cubes at all, of which are all different size.
Oh, wow, wow! I need to go and look that up. That sounds amazing. I love it.
Fact check me, but I think
I
that.
will fact check you for sure.
Is there a way to summarize your PhD thesis in a couple of sentences?
Sure. I think I was trying to. I think a motivational question I've always kind of wondered, and it was a real opportunity to go into the thesis and explore it, is like, what are how much combinatorial strength? This is a question from Chaitin from The Unknowable. How much combinatorial language do you need to be like Turing complete, for example? It turns out you need really very little, you know. And so we start talking about tilings, but it's actually very easy to make a mapping between tilings and computation. And this was done in the 60s. It's very well understood. There's been some great work by Howell in the 80s, which I studied for my PhD. Um, and so it was trying to work out, well, these are all dealing with like sort of finite bounded tile sets. So we have finitely many tiles. We might have infinitely many copies of each of them because to tile the plane, an infinite plane, you need infinitely many copies. But the actual source material itself is finite. And so we understood very well, like that these are for the technical audience, these are signal one and pi one in very regular senses. So these are like very well behaved in a way that we kind of really get when it comes to computation. So tilings of this type are these kinds of computation. And I
So,
wanted to just
so,
lift this.
so is the question, given certain shapes, is the question whether you can tile a plane with them or not? Is that the
Yes, and with what limitations? So you might say, so some people say a tiling of the plane is that every point on the plane has to be covered by some
right?
tile, no overlapping tiles, so they must line up exactly on the edges. And then you can relax certain definitions. So some people say that you're allowed little tiny gaps, and then in the
Right.
limit, those gaps disappear, is the idea. And so I didn't study those too much, but there is a whole sort of plethora of different ways of using this idea of covering, because you have a very natural notion of compactness, where you're trying to sort of find this way of addressing every point on the plane. And what I wanted to do was to show what I ended up doing in my thesis was showing that actually when you lift tilings from having finite language to an infinite language, so they have infinitely many tiles
Mm.
in your prototile set. So you have now, you go from selection and finite selection, and then you make lots and lots of copies. Now you have infinitely many possibilities, and also you have infinitely many places to put them. So you could have a tile set that is entirely unique for every
Mm.
point on the plane. And so there is a class of computable structures which are very well studied, and they are mostly to do with questions of like well and ill-foundedness of infinite sets. So I was able to show that you can have well or ill-foundedness of tiling sets. So actually there's an equal correspondence. As you lift the tilings from having finite prototile sets to infinite prototile sets, that actually it lifts exactly in the computability sense. So that was really quite nice to find, and for that I use things like wired arc reducibility and reductions, which are quite new and quite really quite interesting to sort of look at. So there's different ways of doing like computable transformations because now you have to let your machine run for infinity because you're transforming one infinite set to another infinite set. There's more pointwise is there a computable transformation and how do you actually do that mapping? So it was looking at it wasn't mathematical logic, and that does tend to be the area of pure maths that even other pure mathematicians go, why? Which I think is kind of funny because actually then you bring it back as you said, like tilings are everywhere. I keep noticing them on the floor all over the world.
And if you're a logician, but you're a set theorist, then logicians look at you as like, what? So,
I'm sorry, you need what cardinal with what letter? I'm sorry, what?
oh boy. Yeah.
It's amazing though. I think that this idea of what is this real mathematics and what is a natural kind of way of presenting it, like that doesn't mean to necessitate, sorry, mean to negate the idea of infinity, for example, as long as you kind of use it sensitively. And I think that saying, oh, infinity, therefore we need to use this lemma or we need to use this axiom or we need to do this thing, can be a little bit restrictive. I think the real discoveries come when you get into the skin of why this thing is going on forever, or in what way this process, and thinking about it as a process thing, or thinking about it as a time series can just be thought of as these processes that evolve. And so how do we properly think about that is a very mathematician thing to do. And I think the more we understand, say, or wish to understand, like systems in our lives, like the internet is this vast interconnected system. You and I are talking over it, it's making that work, and some of that is quite applied, and some of it just kind of happened. And it's fascinating, like which bits came where, which bit, how Shannon invented all the stuff to do with coding theory and all the information theory, and then how that's now developing. I'm reading a book at the moment on algorithmic information dynamics by Hector Zenil et al. And I think it's brilliant the way that we can still develop these ideas further forward as we now try and understand this abstract system that we all have in our heads, this internet. It's amazing in many ways, like what just, I don't know, 3 dozen years ago was absolutely an abstract mathematical thing, and now it's in the palm of your hand.
Right. Yeah. I just actually today, for some reason, I opened Shannon's original paper. It's an incredible
Mm.
contribution. Shannon is one of those people that if you go to his Wikipedia page and there's this list of contributions, then it has to be collapsed because otherwise your browser will overflow or something. It's like
Yeah,
most people have
absolutely.
one or two, but like Shannon is like von Neumann and it has like very,
Yeah.
very long. Okay, so that's really fascinating. How did you like I have like several questions about the journey you had afterwards. On one hand, you ended up with quantum algorithms and quantum questions. and then on the other hand, you went into a bank, and somehow you're able to combine these things in your in your life, that you're in a bank and doing quantum computing. So what was the journey? And
I think the journey there is really down to, so I've always been a little bit hacky. It turns out that how I use computers is called hacking. So I didn't really think that there was anything unusual in it, but actually, apparently, it's like, no, you're not using that the way that you're supposed to. And I think that's quite common of a lot of mathematicians I found. So that you find a different way of doing it. As long as it works, it's fine. It's isomorphic, it's okay. So being quite into sort of, finding out how to get computers to misbehave, say, I ended up working
that's
in
another part, by the
cybersecurity.
way, of your another side of your hobbies, right?
Yeah, so I worked for on and off for like nearly 2 decades, like sort of in cybersecurity as like a discipline, as and a field, of an industry. And I've made some contributions on like IoT security, UK government, the Department of Homeland Security, etc., etc. And I've made some contributions on some of the AI stuff. But the quantum stuff I found really interesting because here, I mean, I did a quantum computing course for my master's degree, which I thought was kind of, I remember thinking, oh, this is kind of fun. And then I did a quantum mechanics course and I went, oh, this is kind of fun. And, the mathematician in me is going, oh, this is really well behaved Hilbert spaces, like sort of it's Hilbert spaces on sort of almost Hilbert spaces on safe mode. Because everything's integrable, everything's regularized, everything's normal, everything's great. Great, great, wonderful. It's a really elegant way to describe the universe. And it just so happens that actually, we can use this to approach computation, this thing I'm fascinated about, in a really different way, where we're accepting the stochastic nature of systems and processes and going, how can we get information out using a quantum process, much in a similar way that, if you want, I mean, my analogy for quantum computing is a little different, but like I picture, the Galton board. So you have the big triangle with lots of balls at the top, and then you have a little gate, and then you have a lower triangle with lots of pegs. And so, the balls will hit a peg and go to left or right. And then at the bottom, what do you get? We all learn this at school. You get the normal distribution. So how do you simulate that? Well, what you can do is you can line up every single 3D ball in the simulation with very high precision, and you can teach the model, like physics. You can give it all the physical rules, and then it'll work out what's going to happen at each peg and how it's going to go, and you can get ultra precise about it. And then you set the simulation going, and it'll give you the distribution. Or you can just build a Galton board and let physics tell you the answer, right? And
Right.
actually, that's what we're doing. That's what we're doing in quantum computing. We're just setting problems up in a particular way that we can then just let physics tell us the answer. But it doesn't have to be physics. That's the amazing part. Like there's this incredible field which I find so fascinating called quantum inspired, where you reduce problems to this kind of quantum notion of quantum algorithm. And then what you do is you allow that a representation of that. So you use things like tensor networks or annealer simulations or swarm optimization systems I've seen used as well. And so what you're doing, the proper name there, sorry, is particle swarm optimization. So you could use all these different algorithms, which kind of have this stochastic nature to them, to actually give you hard results, to actually give you like what's usually referred to say as the low energy state, which is your solution. And that's what AI is trying to do when it's doing its gradient descent. Like you're trying to find this lowest minimum. And so
Right.
with a
So
yeah,
sorry, I'm just interrupting. So using quantum physics instead of classical physics, like in your example with the pegs, it's classical physics, and you're using instead quantum phenomena, which we understand
mhm,
pretty well, to solve problems. And when you say other problems like swarm computing, which is like multi-agent systems, right?
mhm.
Is the idea that you reduce those problems into quantum setups, which are then solved?
it's more that you can create a representation. So you're dealing a lot with different representations of the same problem. You know,
Yeah.
a really common class of these problems are called QUBOs, quadratic unconstrained binary optimization. And so QUBOs are basically a sum over all the terms in a matrix and then some particular properties or weights. So you're adding constraints and then you're going iteratively through all of these elements and then you're coming up with a minimum answer. And you can very easily see how that's NP hard because it sounds it, so exponentially many possibilities, all these things you've got to manage. But it turns out that there are some systems, so QUBOs map into a thing called an Ising model or an Ising length model, which I've was learned about in the last 5 or 6 years. I was not being a physicist, but being a mathematician, reading the papers, I'm like, oh, okay, that kind of makes sense, and I can understand what's going on. I sometimes don't quite get why, but that's I usually have some physicist friends who are like, so, no, Mark, it's this. I'm like, oh, okay, that makes much more sense. But the kind of Rube Goldberg machine I've got going in my head. Um,
Right. The Ising model, by the way, was an inspiration for Hopfield networks, which got the Nobel
Yes, the
Prize right
Nobel
now.
Prize. Absolutely. And actually, both of those can be considered versions of QUBO-like problems because you're optimizing this particular setup. And so we find that so if you constrain, regularize a second order quadratic polynomial, it turns out that finding the minima for those is really useful. It's used in portfolio optimization. It's used in pricing algorithms as well. Like there's a lot of stuff that so it turns around and goes, "Hey, I'm a minimization problem. Solve me." And so I think quantum offers a really interesting, specifically for me, it's more about quantum information. And maybe that's, I mean, the quantum computing is incredible too. Like there's this type of quantum computing called trapped ion, which I think is utter science fiction. It's amazing. So like
How is
you
it
could,
called? Say again.
it's called trapped ion computing.
Trapped
So what,
iron.
so what you do is you take, you take a chamber about basketball sized, I'm told, and you make it really empty. And I mean seriously empty, like emptier than outer space. And then just because you can, you make it colder than outer space as well, because we're going for high score points here. And then what you do is they have a mechanism where they can release from the underside of a silicon chip, they can release little plumes, little clouds of just particles, just ions, atoms. And then you can set a magnetic field, which is like this kind of this wave, but you can spin the magnetic field. And so you could create a cup, like an invisible cup, to carry individual atoms, right? And you can control them. That it's literally called the racetrack. And it's like it's just this loop where you can control these little radio frequency cups to move atoms around, like individual atoms. And then we can do computation by just smacking them with lasers.
Wow.
It's
Wow.
incredible. It's absolutely
Yeah.
monumentally incredible. Like this is the level of technology we have. And what it opens up to us from my perspective, what I'm more interested in just because of maybe how I'm wired, is that actually there you can do computation. And you can do computation in a way that actually makes these NP hard minimization problems actually really quite natural. Because again, you just set up the system and let physics tell you the answer.
hmm
Um, and
Yeah.
so, you know,
Yeah. So I think I'm not expert, so you tell me. But I've realized I understand that the power of the quantum computing is that the superposition of the qubits
mhm,
can collapse only to the kind of allowed positions.
yes,
So it somehow enables you to solve NP-complete problems because you just set up your SAT problem or something with the atoms, and then you just let it collapse
yeah,
to the solution if it exists.
yes. There's all lots of if, like sort of if the
Right.
solution exists and if the system can maintain coherence long enough. Usually there's two effects that you use. So you use superposition. which lets you kind of layer these states, these potential output states. And then you also use a lot entanglement as well. So you can have two qubits that are set up. And entanglement actually is really quite a natural definition mathematically. You're saying that the two states of the states of these two particles, these two photons or these two atoms, are in some way inseparable. That's what entanglement means mathematically. Like physically, that causes you to have like headaches from interpretative dances and Copenhagen interpretations and all this other stuff.
It's
But
the philosopher's job.
yeah, that's you can kind of close the door when you need to, because actually mathematically it means that you're going to be the basis of superposition is that you're either in the 0, 0 or 1, 1 state, and you can't have the particles disagree. So when you measure them, and these two entangled particles, they'll either both be up or they'll both be down. And so with that, that's also really useful. With that, you can then kind of affect different particular outcomes, because you have this property in your process as you kind of build this algorithm. So you can use various combinations of these to create knowledge in a statistical or stochastic manner, modulo noise and error. But even there, like the great breakthrough everyone knows about from Peter Shor is the Shor's factoring algorithm. But like the other great breakthrough that mostly quantum computing people know about is Shor error correction. So actually, quantum error correction is a thing because of Peter Shor. It was beforehand. The literature says, no, not going to work. That's not how physics, not how quantum things go. Don't be silly. And Peter Shor was able to line these things up and show, actually, if we do this, we can have error correction. You can entangle, in a sense, you can lock, think of it more like locking different particles together so that errors on one are kind of corrected by the others, by the relationship in this network. So like it's fascinating to sort of see how it's grown as a discipline, and also how I think that is reflexively affecting how we do computation, because it turns out that actually you don't necessarily need a quantum computer for lots of the kind of mid-range cases for sure. Like actually you can get away with supercomputing. I mean, you still have to have a supercomputer, which is a bit of an, with thousands of nodes and, trillions, quintillions maybe of transistors all working in concert for this, 2,500 lines of C++ that you wrote on a Sunday night. But I think that, like there's something really quite wonderful that actually it gives back, which is what I didn't expect. And that's what got me interested, that actually I got back intuition about what's going on, more understanding of like Shannon entropy, and how actually Shannon entropy can be almost as much about what I don't know as an observer, as it is about the uncertainty or unpredictableness of a signal or a system. Like actually you can start to sort of see information theory, when you add the quantum at the front, like you can see it in a bit of a different way. So for me anyway, that's how I have grown to start like Quantum Village, where we're taking like quantum with my co-founder Victoria, like we're taking quantum to just hackers in the desert in Las Vegas.
And what's that? What's Quantum Village?
So there is, sorry.
Yeah, no, tell me. Yeah.
So there is a very well-known big hacking conference called DEF CON. So DEF CON takes place every year in Las Vegas in August, and roughly 30,000 hackers get together in the Vegas sun with unlimited access to casinos and their entertainment. And we talk about tech. We talk about, in our case, quantum tech. So there are lots of, or in other conferences are called special interest groups. So you go to, say, a number theory conference, and there'll be one person interested in the latest developments in Renyi entropy, or there's some particular things to do with, that field. And you go to some topology conference, and there's always someone talk about a miniature track just about developments in a particular area. And what we do is we run kind of the special interest group for quantum technologies, because as I mentioned, they're cool. They're so cool. And then also, like, we're fully aware that if this is going to be technology, I mean, there's lots of hurdles on the engineering side and on the theory side to get over. But like, we're just aware, like, don't keep it up here where, sort of, universities will talk to other universities. If you're writing academic papers, as I have done, and as you have done as well, like, you can write an amazing paper, but, some of those comments in that paper will be restricted in their accessibility. And that's natural for developing a field, and that's fun, good for what you're trying to do there. But sometimes you need to educate people who, for example, maintain computer systems. They need to know about what might be necessary for quantum computing and also what the real threats are, the real limitations of the various algorithms that are being talked about, so that you can make a
Is
more informed decision.
is the idea that quantum computing is going to be used by the attackers on a system, or that basically all systems are going to transition into quantum computing, including the bank itself, and then you have to be prepared.
Yeah, I think both. I think both. And actually, I wrote a paper on using quantum computing to solve defender problems, what are called blue team problems. So actually, we see very much this as a tool that we could use to actually do more interesting things using these incredible sort of ideas that we get. And so how do we feed that back in to, a more equitable quantum society? If we're going to have quantum computers, who's going to have access to that? And how
Right.
are they going to use that responsibly? What does that mean? Like, if you have data processing with a quantum computer, well, if you and I are in the same superposition, Reddit, what does that mean? Is there anything we need to worry about? Or am I just spitballing
Mm.
something that's useless? I don't think we have
Yeah.
the answers yet. So
Right.
really, it's just giving an opportunity to ask the questions, and the crowd at DEF CON are really engaging. We had one quantum computing company come, IonQ, and they brought their device, their box, which was the controller box, and so they took the $10,000 FPGAs out because they're $10,000 a piece. But they also bought the quantum processor. It was like this little gold bow tie and this block of epoxy. It's so cool. Just to have it, you could hold it in your hand. Um, and people were asking all these questions. They said normally we got some feedback, and they said normally we think it's good if we have a few dozen conversations in a conference, but they lost count on day one after 150 about how many deep conversations they were having about technology. And I think that there's a lot of people who kind of have that approach, but without wanting to go all the way into, like, mathematical rigor, which I enjoy and you enjoy, and also people listening will enjoy. And so we're just trying to find out how to engage at different levels. And I think that there's so much for so many different people to offer. And you can see all these opportunities and avenues that actually then when you make a breakthrough on a more theoretical side, you kind of have built the pipeline for that to become a real thing. Going back to your opening comments about, real mathematics, like, actually there's a lot of people involved in that thing, not just the mathematicians. And so I think it's really interesting to approach it in that kind of open way, which again doesn't befit some folk, and that's okay. But I think that, like, you're having open and frank conversations and giving the open and frank answers can have a lot of benefit. And I know that mathematicians are really open and frank, so I think that
Yeah.
we're a natural fit.
Yeah. Yeah. You mentioned defender problems. I don't think I've heard of those.
So there are, like, lots of problems that we don't think of solving, like especially in
Oh, is it?
cybersecurity.
Oh, I see. No, I understand now. Defender problems as in defending
Yes.
from cyber attacks.
Yeah,
Right,
so the
right.
problem I was looking at was actually to do with what's called patch management. So when you have patches for your laptop or your server or whatever, like,
Mhm.
if it's just you and your laptop and two servers, like, you just take 20 minutes on a Friday and it's done, right? And that works. That scales for you and that's okay. But when you've got, like, literally like hundreds of thousands of devices and servers and endpoints on a network, what patches do you apply where? if you draw it as a network graph, and they're called, there is literature about them, they're called attack graph. And so you can map what vulnerabilities on what systems can see each other. So how do you start dealing with that? And so my approach was, quite bluntly mathematical. I'm going, well, rather than trying to enumerate every single part, right? Like that's NP hard, okay? Like sort of working, processing all of that, like you're dealing with a lot of data very, very quickly. It grows exponentially. So that's not tractable. And that's why most people don't consider it as a solution to look at, because it's like, oh, yeah, well, it's hard. It's always going to be hard. So we just do the best we can. But I
Hmm.
wanted to go, how can we ask a more nuanced question? Like, how do we actually, hey, let's look for the most common vulnerability for some sense. We've got these notions of like connectedness and betweenness on graphs. So there's a whole theory in graph theory about it. So it turns out that actually quantum computers are really good at finding, these QUBO problems again. One of them is actually a coding of what an independent set is. So you take the adjacency matrix of a graph, which grows only linearly, and you can code a question which basically says, hey, what are all the nodes that if I remove them, remove every edge? Well, if you've removed every edge, you've removed every chain, every path, every kill chain,
Hmm.
they're called. And so if you remove all the kill chains, then you've improved security. And you've done it by solving an interesting problem that it happens to be potentially solvable on a quantum computer of sufficient size. And so it's kind of changing the
Hmm.
thinking of how do we approach these things in a way that
Wow.
is a bit more, to embrace, this sudden, suppose we do suddenly have tractability of NP hard problems. That's huge. But we're surrounded by NP hard problems that I'm convinced we don't look at because we're like, nah, that's too hard. Nah.
Yeah, it's got this reputation.
Yeah. And actually, like I think there's also cases as well. Like I see people doing papers on like approximation solutions for these things, and I'm like, actually, you know what? If you could get me 90% of the way there, that would be great.
Yeah, the modern set solvers, I think, are pretty efficient.
Yeah, there's some amazing work in I think there's a Google stat solver and there's a Microsoft Z3 which I've used quite a bit. And there's some really nifty code in there, some amazing mathematics.
Hmm. So sat solvers, again, I need to catch up. So yeah, I don't want to lose 90% of the audience
Oh, sorry.
because the more different topics we cover, we have a partition. Anyway, so sat solver, you can write a logical sentence with conjunctions and disjunctions like A
Hmm.
and B or C, etc. And then you can ask which assignments of truth values will make that sentence true.
Correct. Yeah.
And that's a satisfiability question. And it's
Mhm.
NP complete, I think,
Yes, it's complete.
to
Yes.
to to decide to find to decide whether it's solvable or not, like whether there
Hmm.
exists such an assignment. And so many problems like that can be reduced to this. So, for example, this problem of you have a network of servers, and you found out that it's NP complete, for example, or like an instance of it is, and then you can reduce it to a satisfiability problem, and then you can put it into one of those SAT solvers, which are 99% accurate ways of solving these problems in a quick way, which is very impressive to those who
Mm.
know what NP equals NP problem is. Um,
That's
so
a
just a
brilliant
brief,
summary.
brief summary of what we're talking about if somebody doesn't know what is SAT solver, etc. So, so that's what you're doing now at your job. Is that correct?
That's part of it, and there's other stuff
Right.
to do with like how do we deal with the threats from all of this kind of quantum magic. Like sort of if like I mentioned, I think it's called Shor's algorithm, which is a factoring algorithm. In 1994, Peter Shor publishes a paper, and it just so happens that quantum computers should be really, really good at the one thing at solving a problem, and that problem also happens to be the one problem that we rely on for all of our cryptography to be secure. So all the
Right.
security, yeah. So all the security keys,
SSH, right?
SSH, RDP, TLS, they all use algorithms which rely in some meaningful sense on number factoring being hard. And so, we have reason to believe that maybe number factoring isn't quite as hard as satisfiability, and there's lots of literature that tries to work out exactly the strength of it. But we know that for sufficiently large numbers, it's fine. It's okay. Like the curve goes up, and we're quite happy with how far down that curve we are, and it's gone up enough that we think it's hard enough that even an adversary with lots of, like a country full of, supercomputers, have a very hard time, if not ideally an impossible time, factoring these numbers and then reversing out our private keys, because we have this it's called asymmetric cryptography. So we have a public key and a private key. It's all held together by Fermat's little theorem, which I think is wonderful. Like Fermat's little theorem, just like if you've seen that XKCD where there's all this work for everything being supported, and then there's this one little block at the bottom that seems to be carrying a lot of weight. It's
Yeah.
in cryptography, a lot of weight is carried by Fermat's little theorem.
Really? Wait, what's Fermat's little theorem?
Yeah, so for any prime numbers, so Fermat's little theorem is theorem modular arithmetic that states that for a prime number p, a to the p is equal to a mod p. So you can do it
Right.
lets you say things about the relationship between the exponent and a modular group. And there's a
Mhm.
way that you could take this that actually then gives you this ability. The way I explain it usually is like a clock.
So,
So
which is,
yeah,
by the way, not to be confused with Fermat's last theorem, which
no,
is,
not that one, not that one.
yeah,
That
yeah,
one,
yeah. I was
that
at
one,
some point I thought we're talking about that, but okay, but it's basically a number theory observation. It's not a very difficult thing, right? It's
no,
just a simple
very straightforward little
observation,
fact.
but it's
Yeah,
very apparently very. I didn't know that is in the root of lots of.
yeah. There's a little bit of extra work you have to do, but like when you have that understanding of how this modular arithmetic's being put together, then you can build from that what's called RSA key cryptography, and you can use a similar process on elliptic curves to use the algebraic properties of elliptic curves in a like way. So you can kind of have a public and a private number, and under operation of these keys, the to take elliptic curves, the public number will take you a certain way around the curve, and then you don't know how to get back to where you started from there, apart from so literally going backwards. But actually, what you want to do is you want to have a very fast way of doing it. So to complete, you can and get back to where you began, you can use the private number for the private key. And so by using these two components in modular arithmetic, you have imagine the secret, imagine a clock. So you can take it from, you can start going round and you go around to four, and then you encrypt things. And then to decrypt it, you have to get right the way around back to where you began. So the secret might be interpreted as being
Ah.
eight. Yeah, so you're kind of dancing around these modular forms. That's very inexact. I apologize for any
Oh
mathematicians
no,
listening.
that's great. It has to be. I'm imagining somebody driving a car and listening to this, and or creating
Yeah,
a
so the
hazard.
difference is, yeah, so the
Somebody's
real difference, so the real difference for this is that actually there's more than one clock, and that's what makes it secure, right? So,
right.
you're dealing with an exponential um, group as well as the actual numbers that you're multiplying and using. And so with that, you can then encrypt something. And so once you
Is
have the ability to encrypt and then privately decrypt, that's the asymmetry that we rely on for doing modern kind of key exchange. So RSA-based Diffie-Hellman key exchange relies on that to give things that people can look up afterwards. And
is are these examples of what is called one-way functions? And
not
or
quite.
like if I understand right, the existence of one-way functions hasn't been proven at all, right? So, but
No.
or somehow it's the idea there is very extreme, like the function is computable, but the inverse is not computable, something like
Yes.
that, right? Okay,
Yes.
so
Yes.
but these are like approximations in a way to this idea.
In a sense, yes. And a lot of cryptography uses these approximations of this one-wayness for
Mm.
people to utilize it. And so, the magic of key exchange. So we don't actually use these actual algorithms because they're quite bulky, doing all this multiplication, exponentiation stuff. So we actually tend to use other algorithms for actual what's called transport security. But what we do is we use these algorithms to negotiate the actual keys. So you and I will do this kind of number dance with modular arithmetic, and then at the end of it, you'll have a number, I'll have a number, and nobody in the middle, in theory, knows what that number is. There's enough degrees of freedom in all the things that we've exchanged. And actually, we just exchange two bits of information, and then suddenly we know what each other that we both have a shared secret. With a quantum computer, though, in theory, you can factor the keys. So because you can factor the keys, you can decompose them into their component primes. And so there, following on from Fermat's theorem, you can actually work out what was being sent. So you can actually work out what the private key component would be. Because it's generated from these primes. You start off with a couple of primes, you generate a public-private key pair, and then off you go. Whereas with a quantum computer, in theory, you can peek inside these numbers and find out that if this wasn't this huge key, it was two primes dressed up in a trench coat. And so suddenly you can then use that knowledge to work out what the other key would be, and then the private key. And then from there, you can actually break cryptography because kind of the chain is broken. And then you can work out what secrets we expose to each other. And then you can decrypt all of our communications with it, which is usually using what's called a symmetric cipher, which relies on us both having the same key. So yeah, the chain of security relies on number factoring being hard right now. And it just so happens one of the few algorithms we've got for quantum computers, it just so happens to be number factoring.
Yeah, so now this Hollywood movie scenario, what I'm thinking immediately is, so the atomic bomb used to be the thing that who gets it first,
Yeah.
in the Cold War, and yeah, who gets more of them, and etc. So what if, I mean, is that a race? Like, are the military bases of Russia and United States trying to come up with a quantum computer who gets it first so that they can crack each other's? And then the follow-up question, what if they already have it? Or let's say Google,
Yeah.
with all its resources, maybe they have built one already, they don't tell anyone, and they're actually watching us right now.
Laughing.
Yeah.
I think yeah, there is a kind of a super cold war because all these things take place in super cooled dilution chambers. So like there is a super cold war going on in many ways. The biggest difference between, and I think there is actually a either an analyst or even a senior member of the US military who came out and said, yeah, this is as impactful potentially as atomic warfare, in terms
Hmm.
of, sort of how we have secured our world and how we have made it there. I mean, the biggest investors in quantum technology worldwide is China, actually. They have huge resources piled into, sort of world-class universities. You hear a lot about, Oxford and Ivy League, Harvard, Princeton, but Tsinghua is doing just as much like sort of groundbreaking work in certain areas, and so the race is on for sure. I think the biggest difference is that when someone gets an atomic bomb, you kind of notice a bang. When someone,
When they're testing
turns,
it.
yeah, when someone turns on a quantum computer, you can't notice that something suddenly got really cold and really quiet. So which is
It's the
what you have to
opposite.
do.
It's
Yeah,
the opposite of
exactly.
the atomic bomb.
Yeah, literally. Instead of having this huge explosion that you can go, oh dear, there's a problem with that.
And
Like
both are based on atoms. That's so
both
funny.
are based on atoms, absolutely. It's like I think some call it the third quantum revolution that's coming. So that the first one was the quantum theory itself. The next one was which led to the atomic bomb. And then the next one was actually invention of things like the transistor, so understanding how doping silicon works, making semiconductors from that, making lasers. That was another thing that was considered in this the first kind of sorry, the second quantum revolution. And then we're about to have another one because we now have this individual control. So you've got people who have built portable quantum gravity and quantum motion sensors, which are incredibly sensitive. And they've actually to do that they've made portable, and they actually have tested this in airplanes live. A
Where?
portable in airplanes where they can actually detect the movement of the aircraft using atomic sensors. And these atomic sensors are so cold, they're actually in a Bose-Einstein condensate, which is like sort of incredible feat. Not just that you can make that in a lab, but that actually you could make it in a lab you could put in a box and put on a plane.
Hmm.
And the answer there is that, GPS jamming is becoming a thing. It's something like it's either every week or every month, there's like 800 or 900 reports of planes experiencing GPS confusion because of GPS jamming that's going on worldwide.
Hack attacks or what?
Attacks, yeah, yeah, they're sort of picking up on attacks that are going on in theaters of war that are active right now, where they're jamming GPS by sending spurious GPS signals. And of
Ah,
course, they're covering such a large area that, an aircraft being reasonably well like isolated from everything else, they will pick up on these rogue jamming signals and interpret them because it's what it's programmed to do, the GPS. And then it'll change the location of the aircraft. It looks like they're way off course, and they're not. And so there is a whole use case for having quantum sensors. Again, you've built this incredibly sensitive equipment, and now you're miniaturizing it and putting it in. Right now, it's in a briefcase, give or take. Soon, it could well be, in a chip. That's what they want to do.
so
And
so
so,
so the idea would be that you can use that to track your location very, very precisely without
exactly.
GPS. But
Exactly. And then
it's based on integration then?
yeah, so it's yeah, exactly. So it's based on precise knowledge of your momentum and how you're moving. But because it's done in this ultra precise way, the noise that affects regular silicon like MEMS sensors, so normal silicon sensors for motion that are in your phone, rely on very tiny mo movements of wafers of silicon within micro mechanical sort of actuators. And then the chip that you're using detects those. But of course, that's prone to a lot of error. There's a lot of thermal changes, there's lots of other things that can affect it. And so the error grows so much that over a period of just a few days, it's basically useless.
Yeah.
So you have to, go and recalibrate. Whereas,
Hmm.
whereas the potential with a quantum sensor is that actually, you'd be able to not need, you synchronize when you take off, and then you're managed entirely by a quantum sensor during flight. And then when you land, obviously, hopefully everything should line up and everything's fine. But
Wow.
it's a different way of doing it. And that's all from this very precise, ultra precise control that we've gleaned. And we're now at the point of actually going, hey, how does this influence what's going on, in our society, ethically and socially. And also it gives us more avenues as mathematicians to talk about problems like I mentioned that we never would actually think to bother talking about. Because, oh yeah, but by the time you do this, so much error or so much thing or exponentially growing number of possibilities, not gonna bother. I'll just stick to
Right.
what I can get published. Whereas
S-
now, yeah.
That's very interesting. That's very interesting. Yeah, we will get to the topic soon about mathematicians getting out into the world and doing something, and being like, I think you're an amazing example in general of this, that
Thank you.
you're continuing to work really like with mathematical spirit in everything you do.
I try to, and I think that that's a really good way of putting it. I notice, like it comes through with yourself, it comes through with others that I think see this not necessarily that there's this thing we call mathematics as not just, a quaint pastime, as not just this almost self-indulgent thing. Like there's something very true about the way in which a mathematician or mathematics embraces, a problem to find a solution, and how it gives you that solution in a very precise way that you can really understand so much about
mm,
the problem that you never knew before. And that's where you get, whole theories growing from just a few, scratches on a page, or in the case of like quaternions, a few scratches under a bridge, like, you have this, and then suddenly you have this whole field which actually revolutionizes how you can compute 3D geometries and vectors and everything else. And it comes from this very, like, if you look at the way that Gauss and Euler and Erdős, if you look at the greats and you still see how they write the papers, you see how they espouse the idea, there's this sense, sometimes in textbooks it gets lost, unfortunately. That's my one kind of criticism of some textbooks, is that they don't necessarily give you the most useful proof. They give you the shortest or the most like sort of correct or some other parameter. I think that actually I had this when I was studying computability, like sort of, I actually stopped reading some of the textbooks and just went back to the original papers, even though some of them were quite hard to get a hold of, and others were written in ways that I'm just like, how are we, I don't know what's going on here. But actually, in terms of understanding, so there's a complicated construction in computability theory called the Friedberg-Muchnik construction. I spent months on just to really get under the skin. And going back to the original paper was actually, once you got it, it was the floodgates. You suddenly understood why this thing was so important, and why this construction was so like groundbreaking and so useful. And then suddenly you could really espouse like, oh, I get this now. And I think that mathematics has that ability to lead you to those moments. Um,
mm.
and I won't lie, that's a little addictive to me.
Yeah, wow. Yeah, this is true. It's underestimated, I think, to go and read the original work.
Yeah,
Like going to read the original Shannon, going to read
yeah.
the original von Neumann, even Newton.
Have,
Well, Newton
mm,
is difficult because back then they really didn't have any notation, but it was in the making. They were
yeah.
developing analysis in the making, and if you read Newton or maybe some work with commentaries, there's a nice book by Michael Spivak called
Yes,
Classical Mechanics for Mathematicians, where
that's
he
right.
quotes original Newton and then he explains how it works out. And it's just really fascinating how you can see this mathematics coming from these measurements that he was making. And now we have analysis.
Yeah.
Um,
The way that mathematicians, it's really unfortunate, the conversations that you sometimes have where you say that you've done mathematics, because like I there tend to be like sort of people sort of going, you must be so smart. And I'm like, I mean, I'm not that smart. Like I
I
still
hope so.
sometimes, I hope that I've worked enough that I can be smart in this area, but but in certain, if I'm really tired, like I'll still like make a cup of tea and then put the spoon in the fridge and the milk in the sink and the tea bag on my head or something we all have those days, right? And I think that
I think mathematicians are guilty of this more often than other people, to be honest.
perhaps they are. Um, and so like this assumption that this is at the slightly more of a Western thing I've noticed. And well, if you're good at math, it's because you're good at math, as opposed to, well, I worked at it really hard,
Right. Yes. That's
Um,
a big thing that, oh, you're a math genius. You were born this way. No, I actually
Yeah,
do it 10 hours a day.
yeah.
You know.
You catch the bug and that helps. That gives you a buzz and an affinity, I think. But like, I wasn't born doing calculus. I wasn't born doing, sort of studying, sort of infinitary degree structures on Turing or enumeration degrees or whatever. Like I didn't know that. I had to learn it. I had to get it to understand it. The other two kind of common answers are, people who have internalized that they didn't get that far. And so they sort of tell me, I was terrible at maths at school. And
Oh,
it
that's I
really,
get that all the time. I hate
yeah,
math.
that's
Okay.
the other one. That's the third one. Oh, I hated mathematics. And it's just PTSD from this terrible maths teacher that they've
Yeah.
had to
And
suffer,
terrible book. And
terrible book written in this awful way. And I think that's so sad
yeah,
because, like actually there's so many incredible ideas. Every proof I read, there's an idea.
I there was a project. I went to kindergartens teaching mathematics, and we had a
Hmm.
completely different approach. We didn't. I don't think we even told them that this is mathematics, or maybe we did.
Love it.
But I noticed that before the age of 8, but we were mostly going to the 6-year-olds. They don't have that panic yet. They haven't developed this this attitude yet. And we were not doing even any numbers. We were drawing graphs. We were coloring theorem stuff.
Mm.
I did topological manipulations. Some guys made an app where the children could do combinatorics, like shifting colored balls into all the possible combinations and counting how many they get. And that was fun for the kids, and also telling the stories of mathematicians and how they lived and what
Oh, that's
they,
amazing.
you know, and that actually works with children. I feel that if that was the mathematics education of the first 5 years, 10 years, and you can
Wow,
get to
yeah.
deep stuff
Mm.
with this. It will be like I'm not sure why spending so much time just on arithmetic.
I know. And I think that, I mean, why not start getting the intuition for calculus in early, like get away from
And symmetries, group
symmetries.
theory.
Yeah.
Nobody knows that also is mathematics. Tilings. I mean,
Yeah.
we did tilings with these kids. We printed. We had 3D printed Penrose pieces,
Oh,
and they would
wonderful.
assemble them.
Oh, I
Why
love it.
not? Right?
Absolutely. I mean, they're beautiful. I mean, the nice thing about that when you do a lot of mathematics, the nice thing you kind of realize is that it could be as deep as you want. Like and I got this from my supervisors as well. I had a few when I was studying. I started with Barry Cooper. Unfortunately, he passed away just as I started, which isn't great. I don't recommend it. But then I got the opportunity to sort of work with Paul Schaefer at Leeds and also Michael Raskin. And all of them have this incredible kind of curiosity, which I really enjoyed. And also being around other sort of professors there, like Professor John Frost, who's at Leeds, he's a pianist as well. So I used to go and play violin, and then we talk
Mm.
about mathematics, and then we play violin
Oh,
or play
amazing. Yeah.
music, and it was great fun. And actually, if you could instill that curiosity, and that almost that magic about like actually, here's a really cool thing, and then give them the pathway that as they want to know more, they can go as deep as they like, and you don't have to do abstract algebra to understand the beauty of a symmetry set. But if you want to understand abstract algebra, having that core understanding of what a symmetry is, how it can be put together, how commutativity or anti-symmetry works, and then going, by the way, we call this a group, and we call that a monoid, and we call that a magma, and we do this. And it's just learning that there's names for these kinds of things. Whereas before, maybe you didn't care, but suddenly, you can start getting that journey towards that understanding. And I think that's really important what you're doing there. That's really really a very beautiful way to get people to engage from the young before the fear is put in them.
And you can draw a multiplication table for the symmetric group of the triangle, for example. So you just cut out a triangle out of paper, and you mark the corners, and you simply look, if we rotate it this way and then we mirror it, it's this position. And I did this with children, and they get it, and they understand that now there is a different way of computation than the arithmetic one. It's not commutative, but it's finite, but it's natural. It comes from this triangle that we just cut out of paper, and the adult teachers are standing there and scratching their heads. What's going on?
That's really beautiful.
Did you know
that's cool.
that there is a Finnish artist who was amateurly interested in mathematics, and he generalized Penrose tilings into sevenfold and actually n-fold symmetric, because the Penrose tiling is five-fold symmetry.
Yes.
And this Finnish artist generalized it to n-fold,
Really?
and then he was like, hey, I think I got it. And then he contacted a mathematician, also a Finn, and they together wrote a paper where they published it in computational geometry.
I think I saw this, but I don't think I ever got around to studying it. And now you've reminded, I think I'll go find it again. Like I think that's the Penrose tiling is so interesting for so many ways. I've like I love that it's been generalized. I need to go check that because I remember reading about it, for fun, and I realizing, hang on, it was De Bruyne who did a two-part paper on like really deep structures. Like there's only 8 corner configurations for proper Penrose tiling. For example, he shows that each Penrose tiling lattice can be represented as an infinite precision complex number. It's just mind blowing.
Wow.
But he also shows that there are precisely 8 configurations for the corners. And so using that knowledge, you can actually go to any Penrose tiling you might find in the wild. Because what I've noticed, and Roger Penrose talks about this sometimes, like I think it slightly annoys him that people get it wrong. There are some Penrose tilings that don't respect the edge configurations. So with the Penrose tile, with the Penrose rhombi, there's the corners, which have to match up and fill the right space. But then also there are these edge conditions. If you look on a lot of them, there are either circles that are drawn or there's like little chevrons put on the edges. So some have 2 chevrons, some have 1 chevron, and they have to match too. And so using the knowledge of the 8 fixed configurations for, let's call them authentic Penrose tilings, you can tell if what you find in the wild is a real Penrose tiling or not. If you find an invalid corner configuration.
Huh. Wow.
You get there because you can go into the mathematics of it. You can sort of see how beautiful it can be, even in this simple system, this terribly simple system that is just 2 little shapes that lock together.
Originally, I think he had many shapes, right? The first proof,
That's right.
he didn't. And in the beginning, when he published the mathematics, it was not known if this can be found in nature. There was no example, or at least there was no crystal structure found or something. And then they found that there was some crystal structure that
Interestingly enough, at Leeds, I remember I was walking through the physics department. I was visiting a friend, or we were just wandering around, and I noticed there was a poster from a conference on the wall that they presented, and it was on quasicrystals. So for those who might not know, quasicrystals, generally speaking, tend to be constructed, or many of them tend to be constructed from Penrose structures. And this one was constructed in that way. And there was an interesting point on one graph where they were noticing that one of these, they were actually looking at corner configuration. And they noticed they were counting them. Like, I think they were doing it by hand, which is impressive. That's dedication. And they noticed that one of them was occurring more, and they couldn't quite tell why. And I was like, oh, I can tell you why. Because in these eight corner configurations due to De Bruyne, one of them, sorry, two of them are made from a circle of the little fat rhombi. There's the fat ones and the thin ones. And so you can take the thick rhombi and put them into a circle, and you can also turn them around and put them into a circle, and they're both valid corner configurations. And so they'll happen twice as often because obviously of the crystalline structure, they can't tell if it's pointing in or pointing out.
Wow. I hope they included you in the.
I don't think they updated it. I haven't seen anything, but like I think that there's this amazing kind of thing that you can suddenly gain insight on with mathematics, right? Like
Yes. Sometimes
you
it's
can
like obvious to you because you knew this, and then and it's like you're just taking one thing that is known and you're injecting it into another thing that is known, and you feel like you didn't do anything, but you actually did a lot. It's like
oh yeah.
this one marketing expert, I think his name is J. Abraham. Anyway, he always talks about toilet paper. He's like, do you know how many thousands of years people knew what is a toilet and then what is a paper, but they didn't figure out to put them together and make toilet paper? It's like it took
Yeah,
thousands of years.
absolutely. I mean, the obvious is a fascinating subject. Talk about the obvious. Like when I was doing my PhD, there was a fire alarm, and it was in a different department, but everything's connected in me, so you all have to go outside. And so it was in the summer, thankfully. So we were just sitting outside, just carrying on with whatever discussion we had. And while they were clearing out the blocks and doing all the checks and whatever, which took hours, by the way. Well, I mean, I don't know if the checks took hours. We ended up sitting outside for hours. And someone had made a in a seminar, I think it was a set theory seminar, someone had made a fairly offhand remark that, oh, this is obvious in this mathematical thing. And someone just went, is it? And I think it was 3 or 3.5 hours later, the group had kind of come to consensus that yes, it was obvious. But it took 3.5 hours to get there. Like, I think that, it's really obvious. Again, you go back to like NP hardness. Like, sometimes things are really obvious to see when you've got it in front of you. But before you have it, like, you are in a special kind of limbo of infinite possibilities.
It's very dangerous. When I did my PhD, I went through the entire thesis with search, where I say it is easily seen or it is obvious. And there were too many of those, and I really opened up, and many of them weren't that obvious. Nowadays, I have learned the lesson, and what literally what's happening is that I'm writing. And I just notice myself writing these words, and I know this is a red flag. This is a red flag. I'm writing, this is easily seen. I'm like, you're just lazy. You're just being lazy. These are the points where the mistakes usually happen.
Absolutely. No, you're right there. You are right there. There is this the thing doing mathematics is you end up challenging your own suppositions the most. Certainly for how I've sort of come to learn lots of different things. And I always find that, yeah, is it obvious? Are we sure that it's easily seen? Naturally, does it follow? Like, sometimes it is, but you have to go, is it obvious because I've spent the last 3 months of my life looking at this thing? Or is it obvious because, like, genuinely, like, this is, addition, we've done this for a few years, we're okay, we've got it. But I
Yeah.
suppose, even addition isn't obvious until someone tells you, like, 2 + 2 and 4 is always going to work. You're always going to have that. I think, the great example there might be the first part of Principia Mathematica, where it takes 361, I think, pages to get up to Okay, 1 + 1 is 2, guys. We're fine. We're good. We're good.
Yeah, yeah. The set that contains one is not the same set that contains one and two, or something like that. Yeah.
Yeah, that's right. That's right.
That's probably like a lemma before that or something.
Yeah,
Um,
yeah, yeah. I think I
yeah,
tried to like sort of go, I'm gonna read that, and I think I ended up skipping through.
yeah, I had the same experience at some point. And for some reason, it has 666 pages, the first volume.
Yeah, yeah. I think I noticed. Yeah, I mean, at some point you run into the danger of numerology, but hey, spooky, and it's October, so you know.
But hey, so I want to ask this. The relationship between academic and industrial world for a mathematician and related questions, and we can try to go one by one or whatever, but like how do mathematicians market themselves? How do they end up in an industrial world, and how do they find themselves like you in places which are fun and interesting for a mathematician? And I don't know what else, like how else to formulate, but I have like this like an infinite curiosity for me because mathematicians are in academia and they think
Mhm.
that if they go somewhere else, it's going to be boring. It's going to be uh, not so interesting. So how did you find your place? Well, we the cybersecurity story, obviously. Do you miss academia? Do you still publish? Like, well, how do people find this balance? You know?
I think I think I think I do still miss academia on a number of levels. Um, Naturally, when you change environment, going into a more industrial context, or in my case, an enterprise context, there's there's still there's lots of paperwork and restrictions and things that you can't do. I think you have those in academia as well. It's not incredibly different. The metrics are very different, and the requirements can be quite different in terms of like measurement. Like I come up with some nifty code in a computer science department, I might get 3 papers and a prize out of it. I come up with the same nifty code in a company, and I get a weekly nod from my manager, and I move on with my life. I think that you have to, I think to not lose that curiosity can be quite hard. I think you have to keep yourself invested and interested in things. And I think that's where I've kind of been dogged and determined to keep on like solving interesting problems and finding interesting problems and pursuing interesting problems as I find them around me. And it's taken me into corners that I never thought I would go into. I never thought, I didn't think much of quantum computing when I first studied it in my master's degree at all. Like I was like, oh, this is cute. Like, can I get back to computability theory, please? I've got a lemma I want to prove. And I never thought for one moment that actually there's actually a lot of interesting work here, and there's a lot of things that I want to look at and work on. I still feel like I'm settling. I always feel like I'm trying to find like sort of what is going to be next. I think people should entertain that and keep that. I think bearing in mind when you move to doing something for work, you can keep other things for fun. A nice thing about some of the working industry can be that you can compartmentalize things, yeah, quite rigorously. You can set aside days, and you're not going to get interrupted by, say, a teaching schedule or a homework schedule or other things where you have another obligation. But then you have different obligations. I don't think that the difference is that huge. I mean, if you're a mathematician and you go for a job in accounting, you probably will be. There's a higher probability you might find yourself being more bored. Not to say accounting is inherently boring. There's some very interesting corners of it, mathematically speaking, I mean. But those are not quite the rule. Whereas in other areas, if you go towards, I mean, there's more and more companies having innovation hubs, for example, because they've realized that actually, when you're in a data society, such as we are in, then understanding the stories behind these numbers that are deluging staff can be really powerful. But there it comes down to how do you communicate the ideas? That can be a challenge. And then how do you implement them? Suddenly you have this real world sneaks up on you, and you have to enact things. You have to put things into code. But I find actually writing a good Python program or Rust program or whatever, putting together a quantum algorithm, which is still theoretical, but you've got to get it right. I think you've got to. I approach it the way that I try to approach doing proofs. It's just that they're more forgiving. So, you know, the proof has to be right in perpetuity, in every case, in every infinity of possibilities. Your proof has to hold. Your Python script has to work by Tuesday. Like that's a different kind of ask. But I think that I mean, I try and approach it the same way. And I think that's what that does two things. One, it lets me still be interested in a mathematically motivated way. And two, I think it actually makes me more effective because, you know, I'm using this skill that I've spent decades building, and I'm able to use that in a way that is much more like insightful is the word I would probably go for.
Amazing. When you got the job, were you able to explain this to your interviewers, or did you just hack their system and say, look, if you don't hire me, you're in trouble? Isn't that how hackers typically like?
Some of them. I actually did a job for the bank as a contractor. So I did a particular engagement. And they were kind of like, what did you do? And actually, you know, finding bugs and you know, I find there's a lot of mathematical like thought that goes into that because you have to, you know, assume various properties of a system and you know push the limits of that system. So being able to characterize that when the system doesn't exist, it's software. It doesn't like it exists as ones and zeros on a hard drive or in transistors somewhere, sure. But like as an operating system, like these things don't really exist in a way that, you know, my phone exists as an object or as a doorstop, you know, like that's different. So I think having that abstraction layer is incredibly powerful. And I think being able to reason at that layer lets you also, if you talk about it and, you know, as you provided such excellent summaries in this podcast, you know, if you could take a moment to go, oh, just a checkpoint for those who are keeping up, you know, like how do we actually, you know, bring the right details to the fore? And then once you've learned that as a skill, I think it becomes very obvious where your strengths are in a given team. And I think that there's so many interesting and intricate problems that are going to need to be solved in the coming like, decades. And I'm talking broadly about like both the hot topics, so AI, quantum computing, synthetic biology, robotics. They seem to be really big, hot, and interesting topics that I know you're doing some incredible work on with your embodied computation work. I think that this is, you know, this requires, you know, in a very meaningful way, a mathematical approach at least one of the authors on a given work. But I think that when you then have to translate that into industry, it's then okay, what are the bits that you need to explain to an engineer? Well, they don't need to know about these things, they only need to know about these things over here, so that they can keep the system running while it performs the operation that the theory says is going to benefit the organization. So actually having an abstractive thought process and having the ability to go from this kind of, oh yes, it's all about, you know, symmetries on triangles to, okay, here are the rules of the group, here's the thing you need to write down, here's the details, and being able to codify that. It's a huge boost. And I think it's a massively useful and saleable skill. And then it's just being creative about how you plug that in to a job and going, hey, I'm going to try this thing over here. And then allowing it to fail and allowing some people to not get it. But I think that's in common with academic departments too. You know, I've had conversations with physicists and I don't get a good chunk of it, unfortunately.
Oh, then the next person, like I was working when I did my postdoc in set theory, and everybody was a set theorist. But I
Yeah.
could like what this guy is doing, it was beyond me. Like it- I I would go to their presentation at a seminar,
Mm.
and it'd be like, yeah, yes, you know what they're talking about. It's like,
Yeah.
but it's super difficult to follow, and almost always you can't really follow until, even though it's a presentation which was supposed to be to, other set theorists. And I mean, of course,
Yeah.
over time you learn to
Mm.
understand more and more broad range of topics, and hopefully also outside of mathematics. But this is absolutely no surprise that if you go to the other building,
Mm. Absolutely. But
it's,
that tenacity to get it is not unique to mathematicians. I think that most scientists have that. But it's something to be embraced, and it's something to really be indulged, because
mm,
you go down that rabbit hole, you don't know what you're going to find. And I think that when you have the ability to think like that, like some organizations are very easy to let you publish, others and they see the value in that, others are less, unfortunately. But then with the modern publishing model, like you look at what is it, Nature, to have open access in Nature is like $12,000 now or something sky high like this. It's a lot of money. And
mm.
some companies will go, yeah, that's fine, do it, and others will go, sorry, how much? And so you've got to then have a different conversation and sell the value in innovation, and the value in the way in which you can really push your work, and treating your work as a discipline is entirely natural, I think, to mathematicians. And I think they can really capitalize on that kind of way of pushing their own view in concert with the other views. Like you mentioned, you have your view from your postdoc and from your PhD, and then there's other views around, and you don't always get those views, but you know that there's value in there somewhere. And so that presumption of respect and value is incredibly intrinsic to many teams, because then it's like, okay, that person's going to take care of that thing I don't get. And the fact I don't get it doesn't mean it's not important. It's just that when they've done this thing, I can then pick it up and do my thing. And so the way that you see yourself in a team can be really amplified by having that ability to go, okay, I'm sitting here in this process or in this particular system, and then I'm gonna drive home a particular idea or work or research project or code development or minimum viable product or whatever you're working on.
Yeah, learning the language of it often boils down just to the language. Like somebody knows statistics, somebody else knows measure theory, third person have studied probability theory. It's all the same thing, but they use different notation. And then the
Yeah.
fourth person comes from the physics department doing the same thing, and they have their own notation. And somebody has to be able to spot understand the similarity and just be able to
Yeah.
translate. I think
I think
you still can't use ChatGPT to translate between those. Uh,
I mean, I think we've always had that problem. What's it? George Bernard Shaw said of the United States and the UK that we are two countries separated by a common language. And I think that gets more and more true the more people I mean, even between, say, computability theorists and proof theorists, we're doing very similar things, and yet can have wildly different takes on what order you do things in and what a good proof looks like. And I think that
hmm.
actually that doesn't make it invalid. I think I looked it up. I keep track of how many proofs of Pythagoras theorem we have. And I think we're up to like 670 plus or
How
something
do you
ridiculous level.
wait a second. I'm curious. I heard about this, and I'm like, I haven't seen most of those, but how do you say that two proofs are different?
Um, well, I mean, suppose you did something purely algebraic and then something purely geometric. I'd say they're obviously different, to
Okay.
invoke the terrible word. I think that there's different ways of approaching it even within, say, a geometric setting. that are going to use different orderings of certain axioms, or you could take the same axioms and apply them in different ways and you get the same result. That is itself, so that's where the journey of the proof is important. Um, there's
I
there's a
mean, you
book.
obviously can generate infinitely many proofs by triviality.
Yeah,
But it's
so
obviously
we had
not
to
that
ignore those.
somehow.
Yeah, we had
And
to ignore
also
those.
the assumptions, because Pythagorean theorem is so basic that, for example, you can't use distance measure in Euclidean space
Mm,
because it's based on the Pythagorean theorem.
yes.
Yeah, to me, yeah, that's another like point where
I mean,
what
to
is
be
it?
fair,
Yeah.
I think some of the proofs do cheat and they do allow you to use metrics and things. And I think that doesn't help. Uh,
Yeah, I'm not exactly sure. Yeah, for example, the algebraic proof, I don't know what it looks like, but what are the assumptions or what's the definition of a triangle?
yeah, how do you actually code it, and then how do you actually
Anyway,
set
yeah, I
it?
don't know.
There's an interesting book. What's it called? 99 original proofs or something. It's a book of 99 proofs of the same
Okay,
fact about some polynomial. And actually, some
okay.
of those proofs are really inventive. We can find a link and put it somewhere. I'm sure. I remember when I was, when I was really seriously studying mathematics and sort of getting into it, like the phrase that came about a lot was "convince yourself of X, Y, and Z." And that really stuck with me. I don't know about you, but that phrase really stuck with me because it suddenly jolted me into realizing, in quite a deep sense, that actually this is all on me. It's like me putting the effort in to understand something that is, okay, I have this fact. I'm being told this is a theorem. I have this understanding of this proof, and the words make sense in like me being ChatGPT. I understand that these are all words and they all flow in a way that words flow. But then to understand the theorem, that's something different, and you have to work at that. You have to put in an effort to be able to go, hey, actually, yes, based on these assumptions in this particular theory or in this particular setting or context, this thing is always true. Yes, it is. It will always be the case in this situation that a squared plus b squared equals c squared. Um, and you change the context, it doesn't apply, or it applies in a different way, or whatever. But you know what you're changing. Very intrinsically, you know what must have changed. You have a sense for what must have been different for this rigid fact that you know, say Pythagoras, to no longer be a true thing. And I think that that ability to have that internal kind of discussion, that internal, that introspection of discourse is really, really powerful as well. It's probably the most powerful tool I think mathematicians have because
Yeah.
you can't. I mean, yes, you can look out for examples in a forest or on a beach or in a tiled hallway. But at some point, you've got to lift it up and interrogate it and ask it all these awkward questions. Like, why? Why are you square? Why are you right angled? Why is this? Why is that? And then suddenly you realize, oh, yes, it must always be true. Because if it weren't, like, it's not a right angled triangle, or it's not in the plane, or it's, made of jelly or elastic bands or something. And so,
Yeah.
how do you, Mhm.
Sorry.
I say how you get to that point and how you use that internal introspection to really challenge yourself, and then to still yourself come to a conclusion and be reasonably sure that you haven't deceived yourself into believing something.
I noticed that during the several years in the beginning of my math journey, I learned to know when I am certain. Like,
Yes.
I remember in the early years, I did a proof, but I still wasn't 100%. Even though I checked all the steps, I didn't have the feeling that, okay, now I'm
Yeah.
confident. But I developed it later that now I know if I still have that feeling, I know something is wrong. Something I haven't checked every detail, but if I have really understood, I
Yeah,
know.
we're done. We're done.
Yeah.
Yeah. And I remember having that, discussion with so I did a paper which I need to finish and put to publish on doing some things with quantum cryptography, so this whole growing area. And I quite flippantly just sort of put a line in an early draft. I said, "Oh yes, associative, so it's." And I know, and again, I knew that this was right. I'd gone through all the details. I checked everything. I knew it was also secure because there's a way of thinking about things in a detailed way that you can say this is secure or not. And I got to the end of these proofs, and I was like, and I was happy. Okay, this is worth having a look. Maybe I've missed one detail here, but I need to now show it to other people to see what they think about, the broader physical implications as opposed to just theoretical bit. But I remember at least one colleague got a little bit hung up on this associative business. I'd never realized, I'd never thought that actually something always, being associative and always, being swappable in order, to be such a challenging idea. And it turns out, I mean, it's all fine now, like sort of, when you go through, I added a section that did all the matrix calculations, and then it was like obvious that yes, it doesn't matter which way around you do these things. But the challenge that came, I hadn't anticipated, and in a sense, I was slightly frustrated. I was like, but I was also, I was also kind of, in a weird sense, joyful because I was, oh, actually, this isn't always going to be the case in every true system that I encounter. And actually, maybe I am a little bit lucky for having found something that's associative necessarily in this sea of possibilities and states and phenomena that don't necessarily have that property. So yeah, I think that this ability to go, ah, yeah, okay, that's it. That's the one. That's the proof. And to be sure enough that you can show it to other people. The mathematicians are wonderfully irreverent when it comes to wrong answers.
Yeah.
And I enjoyed it. Some people I know may suffer a little bit. I think sometimes maybe some are a little forceful, but I think that actually it's a good thing that we have this openness to discuss ideas and to go, that's not going to work, and here's why. Like with a mathematician, you could always go, prove it.
Mm.
And
Yeah.
they have to, it's the job.
Yeah. Yeah. Exactly. And that's something I miss. Oh, I still do math, but often when I'm outside of that bubble, and I am working a lot with roboticists now and etc. That's what I miss. And also that's what I miss in other life, like politics. I've been listening to politics. I don't know why, but I've been. And it's nobody can obviously prove anything. Everyone just has a lot of opinions, and it's so frustrating to listen to all that because
It can
this
be.
is but I think that's something that mathematicians have to learn also to be able to just relax a bit. Like
Mm.
for me, publishing a LinkedIn post is difficult because it's not a mathematical proof. So I can't like I'm writing something that I haven't proved, let's say. And I have this little anxiety that, what if somebody is going to find a mistake? It's stupid, but it's psychological. Like it's something I think we have to get over. Also, like,
It's it is in a sense you have to learn how to sell an idea sometimes.
yeah,
I think in a math department you can get very comfortable with a good idea just being an obviously good idea. Oh yeah, that's brilliant. Yeah, of course. Um, Outside of context where everyone has the same understanding, when you're in that more when you're in a more diverse team of engineers and people who are project managers and people who are sort of dealing with clients and expectations and developers and DevOps engineers and site reliability engineers. Yeah, there's all these different roles that you're dealing with. Not everyone is going to naturally see that something you're saying is correct or valuable or is the way forward. And sometimes even the best ideas will lose out, and for silly reasons, of budget. is the number one. Like sort of sometimes the universities they have big budgets and they can go, yeah, we'll get this expensive bit of machinery that only three are made in the world. Whereas like in a company, you've got to justify it a lot. So sometimes you have to, roll the sleeves up a bit more and put in a bit more kind of persuasive activity to get things over the line. But I think
Right.
that, the nice thing is that actually you do still know in yourself that when you've written a good paper and you're happy with it and everything's lined up and it's all correct and it's like, so yes, I've taken you from A to B and I've shown you all the important details in between that let you go, yes, this is obviously a good course of action or a good idea or the correct code that needs to be written or the correct system that needs to be built. I think that having that knowledge that you did it right is good, but it can also be a little frustrating sometimes when you've written I've done lots of consultancy where I've done a great idea, a great design, never implemented.
Happened to me as well. Yeah.
It's frustrating. It's
Yeah.
deeply frustrating at times, but I think that you kind of dust off a bit and then move on to the next project or the next idea or the next cycle.
Yeah, that's the opposite from what I said. The opposite where so here you gave an example where you do a nice work and then it's not used or it's not valued for what it is. But the opposite is where you're not allowed to finish it up because you just have to do it by Tuesday, as you said, with the
Yes.
code. And it's good enough is good enough. Like I think that's the mantra that we have to learn sometimes. It's good enough is good enough.
Yeah.
Like it's code
Yeah.
works, it delivers the results and
Yeah.
you
It,
know.
it won't work for the infinity of possibilities, but it'll work for the thousands of customers that have to engage with it. And
Yeah.
that's okay. I think that the thing to remember is that a lot of businesses are themselves processes. And so, building anything is challenging and you're always balancing like the resources with the theory, with the desire, with the drive, with the market, with everything else. So there's a lot of things to consider, and I think that mathematicians do have a lot of tools that make them very good at a lot of things that maybe they think they're not. But I think if they indulge a little bit in what they love regularly, and that's my secret. Like I'm always reading a paper. I try to like read a paper a week if I can, or certainly an abstract and find something interesting. And I don't always have to necessarily find it like as a proof of the book every week. That's not going to happen. But I try and find something. Like I was reading a paper on solving these QUBOs using particle swarm optimization algorithms on GPUs. I was like, oh, that's actually quite an interesting solution. It's not deeply mathematical. I'll probably read a paper like that next week, hopefully. But it was interesting, and it gives me this feeling still that I'm connected to this network of, passionate, thinkers and experts around the world who are we're all trying to build towards like something better and something that is, in a sense, greater than the individual pieces inside.
How do you organize your time? Are you good at that? You read a paper a week, you work at a company. Do you have like a schedule? I'm struggling with that.
I've had to learn to be organized. I started bullet journaling a few years ago, and I found that very helpful. Where you write things out, and then if it's carried to the next day, you change the dot to an arrow. Um, you can invent your own little language of symbols and types that let you sort of deal with it. But I still like sort of forget things occasionally and procrastinate when I shouldn't and whatever. Like we're human, let's get over it. But I think that I think the attempt, I think having a sense of a structure, a sense of a system is very helpful. It definitely helps me. Even if I'm not carrying it out 100%, I think knowing that I just realign, I go back to it, and then I'm like, okay, so what should I try and read next week? Because this week's gone, and I've had a busy week, and I've had to travel for a conference, or I've had to do this or that. And now I'm really tired, and I'm just sitting, on a sofa on a Sunday, wishing I had 3 more days of a weekend.
Mm. There's a professor, one professor once said to me, the reason we make plans is so that we can measure our deviation from them.
Nah, that's good. I like that. I like that. Because sometimes the deviation's the art itself, right? Like sometimes that deviation is actually, oh, you've gone down the wrong rabbit hole, but you found something new there, maybe.
Exactly. Yeah. So we don't make plans to strictly follow them. We make them so that
No,
we have a map, and then we can,
exactly. We can see what's around the other corner sometimes.
yeah.
It's exciting. I think viewing things in that way and trying to find that excitement and that interest that can help spur you forwards keeps you intellectually motivated and active. And so I'm always like sort of wondering like sort of about ideas. And I make thousands of notes about things and didn't work. Okay, fine. But I kind of like sort
Hmm.
of file it away either digitally or physically. And then that's one thing that I learned early on in my PhD and I've carried forward, which is like organizing like your repository of knowledge like quite diligently.
Super
That pays
important.
back. Yeah, that pays back dividend because if you are thinking about things and you make a few notes, maybe you take a photo on your phone, or I use a remarkable tablet
I
sometimes.
have one too.
Um, yeah, they're
I'm
great.
going
They're
to buy the
amazing.
new one. They made
I
the color.
That's right. I just got one. They're brilliant. I love it. I absolutely love it. The colors are so good.
Okay, cool.
Like being able to color code an equation in my notes like makes it like, oh, this is great. This is so much fun. Like it sounds silly. It sounds like, oh, what are you, 12, Mark? No, actually, I
No, I
think it
love
really
it.
helps you. But even there, like on my digital devices, like I have lots of folders and I try and organize it. Is it perfect? No. Do I change it a lot? Yes, guilty. Um, but the point is not that I've invented some universal library system that will last for forever. I don't think I'm that smart. Like actually, it's much more about, okay, what do I need now? So right now I have things for work here. I have it on my work laptop. I have things for my quantum village work. And there's some research projects there. So there's the work for the events we run, and there's the work for the research on my personal laptop. And then I make notes and I read books for many for the research stuff that I'm doing on, say, a Remarkable or even on my phone. And so even there, I have little boxes for like, oh, this is a maths thing, this is an optimization paper, this is a computer science paper. So like it feels sometimes it is the most annoying thing to have to go through like 20 documents that you just haven't got around to organizing. But it can be so important having that mental clarity for what you need to do, that when you really need to push and you really need to have that code ready by Tuesday, you actually do write pretty good code
Mm,
because you've kind of, in that act of sorting out your notes and putting things in the right places, in many ways you've organized the thought already, in my view anyway. And I find that works for me. And so
yeah.
I think, there's some good habits that help you then have this multifaceted intellectual existence that don't necessarily then mean you get bogged down by having 6 notebooks and 5 computers, and just one for each thing isn't going to work. So you have to optimize.
Yeah. Somehow, yeah, I used to be good at this, and then I lost it for several years, and now I went back to it. Just I realized the hard way that if I don't start keep like no notes with tags and proper organization, I will just it's just a recipe for wasting my time, because I do things and then I forget that I did them, and then I've lost the file. I published a paper. It wasn't accepted, but we're going to publish it again. But so what happened was that there was a deadline coming for a
Mm.
conference, and I was like, "Oh, what am I going to do? I don't know. 1 month left. I haven't done anything for that deadline. And then I remember that there was this proof that I wrote like 2 years ago, and I kind of buried it somewhere. I couldn't find it. I remember that I shared it with my friend. I write my friend, do you have my proof about this? Remember I did this? He said, yeah, I have it on my computer in the folder Vadim. And I was like, oh my God, you actually had it organized in your computer. And he
Wow.
sent it to me.
Yeah.
And just adding introduction and the conclusion, we submitted it into this. It got
Brilliant.
eventually accepted only as a poster, and we will make a proper publication out of it. But I
Yeah.
was about to lose it. And who knows how many other papers I have lost this way. I don't know. It's
Yeah. I mean, you do start to wonder about how much mathematics you might have forgotten by accident. You know?
yeah, I and it's like I didn't forget the math because when I remembered it, I remembered I could replicate the proof probably,
Mm.
but it would take me too much time
Yeah.
and why would I if I had already worked out the details and stuff.
Yeah.
Anyway, Mark, I think we have to wrap up.
Yes.
Looking at the time, but this was really amazing. We could continue probably for the whole night and just drink
Probably. But I
coffee
think
and
for now we've given a flavor. So
yeah, we've given a
perhaps
flavor and we should do it again at some point.
for sure. And I can't wait to see who else you have on the podcast and where all the engagement we can get for getting people to think outside of the various boxes. I think that this is really
Yeah,
important. So yeah, let's go. It's going to be great fun.
exactly. Okay. Have a good rest of the week and nice
Thank you
nice
again.
talking to you.
Take care.
Thank you for tuning in for this episode of Manifold Solutions podcast. I hope you enjoyed it. If you are interested in these topics, please subscribe to this YouTube channel for further notifications and have a good rest of the day.